Hello, hi. So welcome to my channel again. So this video regarding the one interesting algorithm, which is the disjoint set, which is a data structure in a if you have covered the graph algorithm, all the topics you must have seen this algorithm. So I wanted to discuss first what is it and where it best fit over the DFS and VFS. First, I will explain what the algorithm it is and where how it optimize over the DFS and VFS and what type of problem it solve. Then we will solve the couple of question related to this algorithm on LeetCode, which I feel like important to ask in an interview, can be asked in interview. That I will pick one up maybe I will pick one, two, or maybe I will pick one, two, three problems which I feel like that I should discuss. I should discuss that problem that I will pick. Okay, so let's first jump into the problem statement. What is this? What algorithm is this? Okay, so disjoint set is a union find. Okay, so I will tell you what is union and what is find. So it was developed to find efficiently dynamic connectivity between two elements. Okay, so basically it is discovered or developed to find the dynamic connectivity. This element can be added at runtime. Okay, so before this, before this means when it was not developed, suppose we don't have discovered disjoint set, then what we have algorithm. So what we have like DFS and BFS. So at runtime, if any element added dynamically, then we will required to like traverse all the element to check whether two element were connected or not. So that could be slow down and it could cause total number of elements or total number of nodes uh, present in that graph. Okay, so it solve the problem, find whether element are connected, or that means are in the same group or not. That the find means we are finding whether two elements are in the same group. I That means they are connected or not. And union means we are merging two groups into one. Okay, so disjoint set is combination of two operation, which is find and union. First we find whether two element is connected or not. If not connected, we will merge it. Okay, okay, so that's two operation we will do in disjoint set. Okay, disjoint set handle these operation efficiently, thousands and millions of items. So suppose if you have thousands or millions of items in a graph. Let's assume you have millions of nodes in a graph, and you continuously adding a node into that graph. Then after adding node, you are checking whether they are connected, any two element are connected or not. It will require what's kind like it will slow down, right? Every time you are checking number of, you are visiting in worst case number of all the nodes. So that is the problem solved by the disjoint set. Okay, so how the operation is union and find. Naive proofs using DFS and BFS would required in worst case can go up to big of n, but union find with optimization. I will discuss what the optimization in this algorithm we will do. So it become near constant for both operation. So alpha n is like inverse Akkermann function, which is give the value less than or equal to 4 for all the practical n. Suppose n to the n is equal to 10 to the power 5, 10 to the power 6, then is near about 10 to the power, near about the 4 or 5. So that is constant. That's why both operation give the time complexity of constant. Okay, when to use? So that's the main things. So if you find any problem, you like go to LeetCode or any find in any new problem, how will you identify which algorithm will fit in that problem? Maybe you have identified that the graph problem, but how will you find out which algorithm will fit in that case? So this there are some key finding. You first find a find from problem whether it's dynamically connection, like edge added over the time. This is the key factors you need to look into that problem. So for where the disjoint set will fit perfectly, need repeatedly check connectivity. Okay, building a connection incrementally where the dynamic things happen, either incrementally or you are repeatedly checking connectivity and multiple merging operation. That kind of signal if you get from the problem, that will uh, help you to find out this is the disjoint set problem. If any static graph means node or any element over the time won't change, then you can simply use the DFS VFS, or you need an actual path, not a just connectivity. So suppose if you find out the actual path from between two nodes, what is the path, how many path, then you would require the DFS and BFS. Okay, so that's the distinction you need to keep in mind while applying uh, these two algorithm in a problem. Okay, so what is the algorithm? Algorithm says like we will find the parent of any when we are finding like whether we need to connect these two element or not, or these two element are connected or not, whether are merging. That two concept we require to find the parent of that two element, like find the parent of A and B. If both parent equal means pointing to same element or so pointing to same node, that means they are in same group, right? So PA means parent of A and parent of B means in same group, means already they have merged, means already they have been unioned. So we don't need to do anything, just skip. Just if parent of A, parent of not equal to parent of B, or you are doing union operation on these two element, then this is the like optimization like I will discuss what is the rank, why I will I am like mentioning here rank. I will tell you in a when I will take an example to explain this algorithm. So if a rank of PA means parent of A is greater than rank of parent of B, then we make parent of B to pointing to parent of A. Okay, what it means, we are like merging two groups in a single group, and we are trying to attaching the smaller tree to a larger tree so that it get balance. Okay, similarly vice versa, if parent of A, rank of parent A less than the parent of B, then we will attach parent of A to parent B. If both rank of both parent equal, then update any of means update any parent of to any and increment its rank. Okay, let me explain how it is works. Okay, so I will have a like written here something. Let me just remove from here. Okay, so let me just ex- explain from sketch. Okay, so let me just reset it. Okay, so that you get it better. So how the union by union and find operation work. Okay, so I will take two array. I will explain why. Let me just define it two array. It depends on the problem statement. Either you would need like array. If it given the problem statement integer, maybe it can be a string or any object. Then you need to like uh, key. You can use the hash map. Okay, to get a mapping. So this is the parent. Okay, this array is the parent, and this is the rank. So let me just put it here. So how parentage means number of nodes present in a graph. Okay, that's the define the parent array size. Okay, so if you see here is the uh, uh, total number of nodes is, if you see 1 to 7, right? So there are 7 nodes, 7 element here. Okay, so let delete it here from let me delete it again and remove, remove. So I think uh, should I able to delete or not? Okay, just hold. We just delete it so that it would be clear. Number of element is equal to number of nodes is equal to area size, right? So we have taken two array as algorithm logic. Okay, so two, one is parent, one is rank. Okay, I will tell you where the rank is used. If we will not use the rank, what happen? Okay, so I will, one array is already require always required is parent. Okay, initially I will initialize number of nodes equal to the array size, that's the parent array size. Okay, initially every element, every node parent is itself. Okay, so 0 to 0, 1 to 1, 2 to 2 means every node or every element. What do you say? Either you call it node or you call it element. Let's call it node at in term of so graph. Okay, so every node pointing to itself, right? Initially, so that's the algorithm say. Okay, so let's keep it 0. Initially all the rank of all the element is 0. Okay, so what it say? It say 1 and 2, there are two groups, and 2 3 4 5 6 7 and 7 7 3, right? So 1 2 means they are group, means find the union of 1 2 uh, 1 and 2. Okay, as per algorithm, just find the parent of A and parent of B. If you find the parent of A, that is 1 itself, and parent of B, which is 2 itself. And as per algorithm, if you see parent of A not is equal to parent of B. Okay, so you can attach one of either, right? Either you can make a parent of B to A or A to B. Okay, so let's define a two nodes. Okay, in a tree form 1 and 2. Okay, and I will connect union means first I will find, I apply the find operation to find out the parent of both element. So if you see parent of both element itself 1 and 2, right? So in case of parent of A and B is different, we can either way connect, make a parent of A to B or B to A. Okay, so if you see rank of both is 0, right? If you see rank initially 0, so 0 0 0 0. Okay, so I have connected. Let's update here. Parent of 2 is 1, right? And once you update parent of B to A, then need to increment its rank by 1, right? Because it's have one element which is 2. Okay, so just increase the one its rank. Then find out once you do union of 2 and 3. Okay, so union of 2 and 3, and if you find union of 2, okay, first I will find out the parent of 2. Parent of 2 is 1, right? And parent of 3 is 3. Both are different, right? So let's attach it here. So how will first I will check if parent, both parent is different, then check the rank. If rank is different, if rank is different, then I will attach to higher rank one, which is rank of parent of 2 rank is 1 and parent of 3 rank is 0. Then attach to 3. Okay, so attach to 1, not 3. Make it, just define one node is 3 and it will point to 1. Okay, so updated here, correct? So let's do operation for 4 and 5. If you find out 4 and 5 both parent is different, 4 parent is 3. Okay, correct? And 5 5 parent is 5, correct? And if you find out both parent is different, right? let me let me just, okay, so if you see 4 and 5, 4 parent is it should be 4, right? Initially it should not be 3. I have written a wrong number, so let me just define it here. 4 and 5 both have parent 4 and 5, and 4 means pointing to itself. So let's connect 5 to 4. You can connect either way, but I am just connecting to 4 and 4, 5 to 4, and updating parent of 5 to 4. Okay, and also once you update the parent, you need to also increment its rank, which is 1. And well, go to the 6 and 7. If you find 6 and 7, that's a different. 6 parent is 6 and 7 parent is 7, means pointing to itself. Just put it here, and where is the 7, 6 and 7, and I'm just updating parent of 7 is 6, and let's update it here also, and increment is rank also. Okay, and once you see here, last group, which is 7 and 3, if you find rank of 7 is, means parent of 7 is 6, right? Which is rank 1, and rank of parent of 7, parent of 3 is 1, which rank is 1, both rank is 1 1, right? Then we can attach any one of them. So I will just attach its parent to it, and just once you attach with the same rank, just increment its rank. Okay, so so far now I have connected all the I have connected all the groups, right, as per the logic. So if you see, one group is 1, 2, 3, 6 and 7, all these are connected in one group, and 4 and 5 is connected in another group, means there are two connected component, if you see. Okay, means two separate group. So if you see what is the optimization here, first optimization I have already done by the rank. So rank help, suppose if you have a same rank of two element, means parents. So you either connecting to each other, right? Either you are making a parent of A to B or B to A. That's you have choice, right? But if you have a different rank, means suppose if you have a parent of A rank, let me just write here, rank of PA is greater than rank of PB, then for optimization only, so that it don't become skewed type tree. Okay, in case of merging, so you just attach a smaller tree to the larger tree, means this is one is smaller, this is one larger, it have larger element, right? So you just attach to this parent, so that find it find it by the rank, total number of connected component, to get the rank count. Okay, so and union path compression, that the second optimization, union by rank plus path compression. Okay, so what is path compression? Path compression is whenever you finding parents. If you see this here, parent of 7 is 6, right? And parent of 6 is 1. So ultimate parent of everyone is connected here is 1, right? So suppose this is one smaller one, right? Suppose if you have something like this one, okay, this is 8, and somehow this is connected to this way. Okay, if you apply operation and you get this type of uh, tree, then this is seems of skewed, right? So if you finding out the find operation for 8, suppose you have if you are doing merging operation, if you're finding out the operation, find the parent of 8, you will first it go to the 7, go to the 6, then you raise to 1, right? You are iterating, you are visiting 3 elements, right? So that's the like maybe in worst case you visiting the all the element, right? So in path compression it says whenever you are finding parent, you just update it to the uh, main parent. So instead of linking to this parent, you just link to the main parents. So just remove from here. Okay, and let me just, if you suppose we have a two element, just do it, link it here. So by logic I will tell you how it will do. So if you find out the parent, right? So how will you find out the parent? If you find the recursion logic, suppose if you have parent, how will you check parent you not is equal to you, means this is not pointing to other, right? So what you will do, you will just recursively go to the its parent, right? Which is the this one, and in last you will returning either you. Okay, so that's the, and path compression, you just updating once you find the actual parent, you just update for each element, you just update the to root parent instead of connecting to. That's the optimization in we will do in path compression. So that's why in worst case or average case, in all cases it do the rate it time complexity near constant. Okay, so that is the union, but that is the disjoint set and optimization with the union by rank and path compression. So this is all about the this video. I think this is already